MF should be as large as possible. Of course, if you are doing a very high power drive, you may not be able to, using IGBTs, you may not be able to have a very high frequency of switching. But if you try to have very high MF, then this becomes less of an issue. We have a demonstration number 7, and we will do that in a second. What we do here, all right, let's see if I can, now I don't have any more T sessions, so hopefully this will work. We're going to AC inverters, demo 7. Okay. Now this one is not a closed loop system, but you could easily make it. So you have essentially same setup as before, except that the control voltages here are sinusoidal, and we're using the same PWM block as before, and we're using both of these to drive the inverter, and then the motor has got sinusoidal back EMF voltages. So it's a pretty simple, straightforward model. And then we have got again inductance and the resistance in the parameter file. So let's look at the parameter file real quick. So it's got very few parameters, so making it simple. So we have got okay. So the frequency is 47.62 hertz. This is the frequency of the rotation of the motor. Back EMF about 70. We have a phase lag of minus 15. So if you look at the motor, we have a theta here. So that's a phase lag of minus 15 degrees. Okay, and we have got.
Is this motor an induction motor? What does it represent?
An induction motor.
Induction motor.
Yeah.
There's no torque. There's no electromagnetic torque.
No. When we get an induction motor drives, then you'll see do things quite differently there than we're doing here. This is just to illustrate the three-phase sinusoidal inverter. So we have got 1 ohm resistance here, 12 millihenry inductance. And then now, one thing interesting we have done is change the high and low from +2 to -2. You only need 1 volt to turn on our switch, and we have made it from 2 to -2. So this way we avoid having a delay because the transitions don't overlap too much. If you have high voltage, then transitions overlaps. That way we can avoid a shoot through. If you have a shoot through in simulation, then simulation is going to get give you wrong results, right? So here, to avoid the shoot through, we have done 2 and -2. Here we have MF of -20.5, and the PWM frequency is calculated as MF times frequency. And gain is 500 for the PWM generation, and we have set the amplitude modulation to 0.9. Okay. So this is the inverter, and we have got essentially 400 volts on the DC bus. All right, so let's see. So you can run for 100 milliseconds, and maximum step size is 10 microseconds. And let's see, we don't really want to run a parametric speed. This is demo. tea break. Okay, so let's go ahead and let's see here. We're going to plot. PWM signals, which vary sinusoidally. And we can also know this is going from -1 to +1. Okay, and then if I plot also the bottom switch, change the color of this so I can see this. Okay, so they're complementary. I can expand it a little bit more. So you can see that they're complementary. If I zoom in here, their overlap is not too much. So you avoid shoot-throughs. If I were to plot the input current, this is my input current. We can plot it. That's how your current looks like.
And are those spikes real spikes or
imaginary? Let's see. Let's see.
you can expand it a bit more?
Let me expand it to. One more. That's your current looks like. What do you think?
Is there a reason for those spikes in the sense from the circuit?
Point of view? Let's look. I mean, the only reason those spikes can come in is
Another one on the same.
yeah. So plot. Those are actually the spikes which are happening because of shoot through. Let me actually see. Let's plot this. 1 second. Let me plot. Let me delete this and add PWM. So you have got have here you can attribute this one to this shoot through. Right? So, and so you have a slight, I think you still have a slight, so you need to put an offset or dead time between them. And I think the other ones are attributed to the other legs. Yeah. So you have the current spikes up almost by, in that nanosecond time. Yeah, so you have got this one. I guess there's nothing here. So when red is going up and green is going down, we have shoot through here.
When the lower one is going into conduction, that time it's going to be true.
That's correct.
In the lower one.
Yeah. That makes sense, right? So when the bottom, A bottom is going up in conduction, then this spike happens. Yeah, correct. Okay, so that was good exercise. All right, what else we want to see here? Let's plot. Now the harmonics, there are two important voltages you look at harmonics. One is the voltage between VA and this middle point of the inverter, and the other one is VA and the neutral of the phase to the neutral of the motor. So we can look at these. So we can insert voltage probe between the motor side. Let's look at this voltage here. So that's your inverter voltage, phase voltage, right? And we do FFT on this. Okay, so this is an interesting pattern you have on the FFT side. Now, here, these occur, obviously, you have the rotational frequency which we set. Let's see what we set there. 47.62 hertz. That was the rotational frequency.
What is switching frequency?
Switching frequency is 20.5 times 47.62, which I think is about 976.21 hertz, right? And so you have got harmonics. So 976 is somewhere in the middle, but the middle harmonic is missing, but you have the side bands here. And here also you have the side bands. And let me just see if I can. So the voltage here on the top, this one here, let's look and see what that voltage is. peak is about 179, 180 volts here. So which is in line with, we have an amplitude modulation of 0.9. So 0.9 times 200, that's where it is coming out to be. And then these frequencies which occur, basically you have, the formula is essentially MF.
Plus or minus 2.
Yeah.
If MF is 40.
Right. Now here, in this case, it's 20.5. It's not odd integer, but still the same as applying here is, if you look at this frequency here, so you've got about 879 hertz here. And if you look at the other one, pardon me?
It should be 1000 plus.
Yeah. Right, so anyhow. So one interesting exercise to do here is to, in order to evaluate the harmonics, you can play with the value of MR. So one of the exercises we'll do is run a parametric analysis on the frequency modulation version. Right, so let's get back here. All right, so this is one of the parametric analysis which we could do, but since we're running out of time, let me expedite it. And here is this one here, what it shows is motor voltage line to neutral. So you have got obviously the side bands, MF minus 2, MF plus 2, which is what you were referring to. And then the MA V in by 2 decides the amplitude of the voltage. Okay. And moving forward, now this one here is an inverter voltage line to midpoint. Here you have got MF component, and then you have got the two side bands, MF minus 2 and MF plus 2. Either waveform you look at is gives you similar information, except that when you look at line to neutral, then you don't have the middle point. Because that middle component gets cancelled in the neutral.
So the earlier one is what you have shown. Is it line to line or is it?
That's line to neutral. Yeah, line to neutral. This one is line to neutral. So your middle pole here is missing. And here you have line to midpoint, and you have got this big middle pole here. Now here, one of the interesting part here is we actually ran the analysis of 20.5 and 21. 20.5 being not an odd integer. However, the results were not that dramatically different, and the reason is that still MF is large enough number that you could still apply the same principles.
You mentioned there that MF must be integer
Right.
to eliminate subharmonics. But how do you achieve that when you are having a variable frequency? I mean, if you can vary it from, let's say, a few hertz to 60 hertz or 70 hertz.
Your question is, yeah, I think when you have a variable frequency, you can't do a whole lot except make sure that, number one, MF is an odd integer, right? That's number one. And number two is that MF is large enough. If MF is large enough, let's say if your frequency range is up to 50 hertz, right? Let's say you go from 10 hertz to 50 hertz. And if I can have MF where I have a switching frequency of 20 kilohertz, you really don't have to worry about any part of it. Right? At that point of time, you are above all the theory. So if your MF is large enough, then these rules are less applicable. Right? And plus the harmonics are so far off that they will not really matter in the actual performance of the motor. But if the let's say you have a high power drive and you can't afford to switch at 20 kilohertz, you got to switch at very low frequency. In that case, these rules become a whole lot more applicable, right? So you want to say, okay, at that point of time, it becomes critical to have MF large enough that you don't have subharmonics at the low frequency. If you set the MF to be, let's say, 9 or 5 or 4, then you're going to have subharmonic in the subharmonics in your motor. But the trick is, how do you don't have? It'll be nice to have it variable, but you can't really have it variable. All right, I think this is an example. We will not run this demonstration also since we are running behind schedule, but to give you an idea here, so here you have a low frequency, 10 hertz, and then your MF is 20.5. Here still MF is not large enough, and consequently your PWM frequency is very low, 210 hertz, 205 hertz, and so you begin to see subharmonics in your plot. Okay, and so the subharmonics available is there both for motor. Well, they're pretty much reflection of each other. Motor voltage line to neutral, and inverter voltage line to midpoint.
Why is this number 21?
Why number 21? See, the number when this comes from University of Minnesota Lakes. That was one of the theory which was proposed by Dr. Mohan. Yeah.
It's on, it's still
No, it should also be divisible by 3.
3. Yeah, but even 18 can be divisible.
Yes.
But it's not odd. It should be an odd integer and divisible by 3.
Right.
Then only the harmonics are less.
That's something.
But again, variable
27.
frequency you cannot have all the
27
time.
again.
In the
27.
Variable frequency, that frequency will keep on changing, and if your PWM is constant,
Right.
at some point of time it's going to go even.
So less than 21 would have been a number like
Yeah, you cannot.
15
You cannot have it. You cannot have it.
That becomes then too low frequency.
I think here the trick is if I can have it MF is very large, then none of the rules really apply. But if MF is very small, then of course you're trying to optimize the system. Okay, what can I do to optimize the system? Okay. All right. We're going to skip that also. Here was the parametric sweep 9, 14, 19, 24, and then this is where you can begin to look at your harmonic analysis.
So this is the parametric sweep.
Yeah, this is the parametric sweep, that's correct. And in your CD also there is PDF of the presentations. You should be able to see in color all the graphs. And here is a nice parametric sweep. Let's see here. This one is demonstration 9. Yeah. So you can see all the theory behind it. MF plus minus 2, where MF and then 2MF plus minus 1. So the interesting part here is, so here you have odd harmonics, 1, 3, 5. Here you have 2, 4. Here you have 2, 4, 6. Here you have 1, 3, 5, 7. So that's the theory behind this stuff. Okay, overmodulation. So overmodulation is where we actually take the amplitude MA to more than 1. Now when we do that, what happens is your duty cycle now is clamped at 1, right? So when I'm looking at my limiter, I can still set my limiter to 0.95 so that I don't have issues of burning the FETs. But the command from the control command stays at 1 for a longer period of time. So here I think I can show you, this is how it works. So when I have a amplitude modulation, let's say if I set it at 2.5, then my duty cycle command stays at 1 for a longer period of time. Right? So this is what you do in amplitude modulation. The theory in amplitude modulation